All right, and so this makes sense as a natural generalization of the software perspective on labeled transition systems and modular reasoning. But I also mentioned this operator should enforce that there are no duplicate calls to the same method, even if they have different arguments and return values. And here's the reason for that. We have to ask ourselves, what does the method that we define wind up looking like in the physical circuit that we're trying to synthesize eventually? Well, let's say I have method F, which is going to have just one set of input wires standing for the arguments to that method, and then one set of output wires giving the return value. So in other words, one method turns into one physical circuit sitting there in two-dimensional space on our larger board that has input wires for the arguments and output wires for the results. And then imagine that we have, say, two different other methods out there. Here's G, here's H. They have their own inputs. And imagine what would go wrong if we tried to get G and H to both call F on the same clock cycle. The way this works in practice is we have what's called a demultiplexer that potentially, let's say, G and H both contain calls to method F. They will send out on wires the arguments that they want to use in those calls. They'll feed into the demultiplexer, and then we'll have the scheduler that tells the demultiplexer whether it's G or H or neither that gets to provide the argument to F on this cycle. But it's at most one of them. And then the output here can effectively somehow be fed back into G and fed back into H. And actually the scheduler is deciding whether G gets to run on this cycle or H gets to run on this cycle. And the point is, however we make this work, there's just one set of wires for the input to F, and we only can have at most one useful thing that we put in there. Another weird thing about hardware is probably F doesn't get called on every cycle, but the circuit's always sitting there on every cycle, so it'll just compute garbage on cycles where we don't even bother to decide what its input is. And I think somehow it's just cheaper to allow this to keep happening than to worry about shutting down the power to one part of the circuit, though there are techniques for doing that. So I hope that explains why this operator should enforce at most one call per method, because the calls are competing for finite resources, for physical representation of the inputs to the method. Okay. So I'd say this is the big ideas about the semantics and implementation of BlueSpec. Any questions here before we get into how we state theorems and prove them? All right. Let's see. I think I'll have to reuse some of this. So I want to just draw a diagram of the first example that I'm going to try to do, and we'll see if we get through the whole proof of it today. There's probably just about the right amount of time. So this is going to be a simple pipelined producer-consumer system, and I hope when I draw this picture it'll be sort of intuitively clear what it's referring to. So this +1 box is a component that's just going to keep sending out natural numbers increasing starting from 0 or something like that. Where does it send them? On every cycle it sends them into a queue, which I'm drawing like this, where the open end is what you NQ into, and the closed end is where you DQ from. And then I have another box that tries to pull out of this queue, get a number, double it, and then enqueue it into another queue. And then finally, I have another box that maintains an accumulator, and every cycle that it can, it dequeues from this queue, adds it to the accumulator, and then something like outputs the old accumulator onto a serial port or something. So this is a system where potentially on every clock cycle, all three of these boxes are active, and the queues are kind of mediating between them and orchestrating this parallelism. It turns out, just thinking in terms of the analogy with this software level view of things, imagine I've defined a reasonable refinement operator following the same kind of theory of labeled transition systems. Then we should be able to show all this is equivalent to a system that gets rid of the queues and just does all the steps together in a single cycle every time an input pops into the system, and then sends the same output. So these queues themselves become like the private channels that we were hiding in the software version of things, and they're gone. We don't have to think about them in relating to a natural specification of this kind of system. Does that make sense? I'll show the code that's a little more concrete about this in a moment. But the basic idea is collapsing pipeline stages that are connected together with queues. We should be able to prove this in a pretty broad way. Question, yeah?
Do the queues not have like different like throughput implications than like the raw ticket channels, or like whatever plumbing them directly would do?
So there are scheduling decisions related to the fact, for instance, queues can fill up. You might so in this case, it will be true that every one of these three boxes has the same processing speed. Every one of them does its work in a single clock cycle. In more complicated examples, that might not be the case, and there might be rate mismatches across the stages, and we'd rely on back pressure in the queues to tell a stage, don't send me something new yet, I don't have space. And the BlueSpec compiler automatically schedules that, so it works out properly. Because in effect, methods can have preconditions where you're only allowed to call it if the precondition holds, and the scheduler makes sure preconditions are respected in whatever schedule it chooses. All right, one other ingredient I should mention that we'll need to understand what's coming next. That is inlining, which is a very unmodular thing, and we'll see why we want to use it to, paradoxically, to make modularity appear. Just to write a simple, concrete example of inlining, let's say I've defined module M1, which has one register of type int, and it has one method called f that takes in an integer and returns void. All it does is it adds its argument into the register. And I'll give us module M2 as well. I'll say this one has a register called n, which is an integer, and it has a rule. It says M1.f gets called with n, and then we'll increment n. I'm going to need to get some more space here. So we take those two modules, and then if we compose them together and do inlining, then we're going to get a single module. And in this particular case, what we would get is module, I'll call it module M1, M2. You might be able to guess what the result looks like. I have all the registers of the two original modules jammed together inside one module. So R and N are both there, and the method disappears. Instead, we just inline its contents at all the call sites. like so. So this is the result of an inlining composition of those two modules up there. Any questions on the mechanics of how one performs inlining? Does anyone have any ideas on how in a good proof that takes advantage of modularity we might want to appeal to this operation? Yeah?
Can you use this compositionality lemma to show that certain kinds of intramodular optimizations are valid or don't alter the underlying behavior of the system?
That sounds right. So if we want to use this to prove that intermodular optimizations are valid, we could have a system that's naturally expressed as a bunch of separate components, and then to simplify the analysis, we can smash them all together and then prove that some correctness property holds of the smashed together version. And then that result lifts back into the separated version. And so what we might generally do is if we have a spec that is monolithic, like this one, we might sort of run inlining backwards to split it into two separate modules so that we can then start doing proofs separately about each of those two modules. We can introduce modularity where it didn't exist before by running inlining backwards, and we can prove a theorem saying running inlining backwards preserves the semantics of modules. So it's kind of a prelude to starting to use congruence properties to reason modularly about the constituents of a design by breaking a monolithic thing into a multi-part thing with reverse inlining. And that's what we'll need to take advantage of in the proof of this pipeline in some parts. All right. Any last questions before I bring...
When you do that, you're creating the method F. You want to have a hide around that so nobody else calls F.
Right. That effectively shows up here. The rule is when I guess this isn't directly talking about composing modules. When I compose two modules and one calls the other, then the caller becomes the sole owner of the wire for the method that's being called, and it's no longer available for anyone else to call. All right, so I think I'm going to bring back the screen unless there are any last questions where the blackboard is crucial. All right, here comes the screen. So here's another file where now this is going to be the first one where we actually really get into using the Kami framework and not just a few little parts of it like the bit vectors definitions. And I'll fast forward through most of this. Feel free to poke around some of this afterward. But here's one concrete example of module definition. We saw a shorter one yesterday. So what I do first is I'm going to essentially prototype an external method that I expect my module to be able to call. In particular, it's for a module called FIFO1 and a method named enq for enq, and it expects an 8-bit number as input and returns nothing. Given that, I can define this module that takes in, well, it has a register. There's an 8-bit number called data. It's initialized to 0, which is the default for that data type. It has a produce rule that reads the latest data into a local variable and then uses that local variable to call the enq of the q. And I'll kind of interchangeably say q and FIFO here. I think q is the more common software term, and for whatever reason FIFO is the more common hardware term. And remember, we learned about parametric higher order abstract syntax yesterday, where there was a special constructor to inject variables into the broader type of syntax tree. The pound sign is the notation for that here. So Kami is using parametric abstract syntax, and when you mention a variable, you have to put a pound sign before it. So I call enq with the data, and then update my data register to be one higher than the original. I'm using $ for injecting literals into the language. Then I have just a little dummy return void marker at the end. And I'm also providing a method that takes in a new value from my register and then actually drops it in there. So again, this is using Cox's lovely extensible parser to give us halfway reasonable syntax that almost looks like what you'd define from scratch for a freestanding programming language. Any questions about this syntax here?
So the return is because the return V is because of the limitation of the extensible syntax.
I don't think that's it. Even at the level of abstract syntax, we decided to simplify things by requiring there's always a return at the end. Yes?
Can you explain the method signation? I mean, what is these two strings and the double hyphen?
The double hyphen is separating module name from method name. Question, yeah?
When you define the syntax, are you defining a bunch of operators that just happen to add up to this module, or are you defining a whole parser that parses everything down to the period?
Well, we're registering syntax macros that expand all this into elements of inductive types of syntax.
So is this one syntax definition that you use there, or did you define a bunch of operators?
It's separate macros for different parts of the syntax. All right. Yeah, so it is possible to add new macros later and effectively extend an embedded language like this one. So let's see. This is just a bunch of pointers to some definitions in the library, but I'm going to stick to our intuitions from the Blackboard in this case, and just get into the example. This is the three-stage pipeline system that I was showing before. Cool property of this development, similar to our last one, it's going to be actually an infinite family of pipelines, parameterized on a valued data size that tells us how many bits are in each integer that flows through the pipeline. So now, I will prototype a method in FIFO1, the enqueue method, that expects an argument that has as many bits of input as this data size parameter tells us. And then stage 1 of the pipeline, which I drew as a little +1 on the board, has a register with data size bit integers. And the only other content is a produce rule that's ready to run whenever the scheduler lets it, that will read the latest data, enqueue it, and then increment data. By the way, this enqueue call might not be legal to run if the queue has run out of space, and then the BlueSpec scheduler makes sure we don't actually run this rule in that case. That's an important kind of modularity that really saves us time in developing and reasoning about code. We don't have to think about timing, connecting components in a system, which is apparently a big time sink in traditional hardware development. So this is one of the 3 stages of our pipeline. And I suggest to Calc afterward that it should consider unfolding these definitions as they appear throughout our proofs, and some of the tactics in our library will take advantage of these hints. Okay, so let's look at the second stage of the pipeline. Now it's going to try to dequeue from FIFO number 1 and enqueue to FIFO number 2, so I'll prototype both of those methods here. And then down here, our second stage has a do double rule that dequeues from the first FIFO, computes 2 times that number, and then enqueues it into the second FIFO. So this rule could be blocked from running if the first queue is empty or if the second queue is full. But again, we don't have to think about that here. That will all be handled for us by the BlueSpec compiler. Finally, the exciting third stage is dequeuing from the second FIFO, and then in the end, there's just some output to the world method called sendac here, which is the sink of all of our data flow. So this component has an accumulator of the same size as the inputs, and one rule